So welcome back. Let us continue. And as we mentioned it last time, we'll be discussing further the properties. Let's put it like this: properties of G spaces. G spaces. And let me put my glove because it's kind of difficult right on the tablet with the sweaty hand, so now it's going to be better. So recall, here we are discussing the case when G stands for a compact, so this is a compact Lie group. And we are basically collecting all the necessary facts from the equivariant topology, and we will be using these facts in order to develop an equivariant version of the degree theory. So let me recall that as we were discussing before, so suppose X is a topological G space. So we have here an action of the G with an action with G action, and I believe I was using this notation. This is G times X to X, and we'll write, as we mentioned earlier, Gx just simply as the Gx on the element X. So let me introduce maybe some additional notation before we move forward. So we'll do the following things. So let me denote, let's say we also put, and I put here like this. I will denote like that phi, and I put here G semicolon X, and this symbol will stand simply for all the conjugacy classes H, that are belonging, and we know that's the notation. We have the set of all possible conjugacy classes for the of closed subgroups in G. It was denoted by phi. So here we will put it like that. That this is, there exists an X in X satisfying the property that H is equal isotropy group of X. So what it means? That means that which means that this symbol 5Gx stands for all orbit types in X. So if we were to be saying that, if you were to be saying that X is a G space with the finite number of orbit types, with finitely many orbit types, so that would mean that the cardinality of this set, represents the number of the orbit types. So those are the this is the number of orbit types in X. And also, just for the simplification of some proofs that we don't really need the most general case where X is a general topological space, we may assume that we will let us assume that our topological space, that X, that means that G space X is a metric space, is a metric space. That means simply we have here a metric that defines the topology on X. Then, of course, now we can return to the previous property. Remember, last time we finished the lecture when I, in a certain way, got stuck trying to optimistically overdo the properties. Means starting, I started the proof, realized no, it cannot be proved like that. So maybe write it down like this: proposition, maybe proposition. Let the metric space XD be a G space. So here is remember here, as always, G stands for a compact Lie group. And A contained in X, maybe write it down like this, and H is a closed subspace, subgroup over there. 10. If XD has finitely many orbit types, finitely many times. Maybe not nice form. Okay, just simply write. Assume. Just simply write it down. Assume that XD not nice. No. XD XD has finitely many times. So finitely many different orbit types. That means simply that this set phi G, and then we have here X, so I put here cardinality is smaller than infinity. 10 XH, which is the specific subspace, let's say the subspace of X with the specified isotropy groups of the elements, namely H, then is an open set in XH. Oh, that's kind of the statement we started to prove last time. So we begin with the lemma. Under the same assumptions, so that means for a metric space G, for a metric space X D being a G space and a closed subset A contained in X, the set GA is also closed. Indeed, that's a simple fact, proof. Now we can use the fact this is a metric space, so we know that in such a case we can describe that the set is closed if it is sequentially closed. So that means suppose that Gn so such that Gn belongs to G and An belongs to A is a sequence such that, and here we have Gn An converges to a certain point x naught, we need to show we need to show that x naught belongs to the GA. Yes, that means we will prove that GA is sequentially closed, so it's closed. Since G is a compact manifold, manifolds are metrizable, so the same thing, so that means in this case you can just simply say that, okay, since G is a compact manifold, we can assume without loss of generality that, okay, that Gn actually converges to the G0 by compactness. Then, clearly, we are getting, by applying to this particular sequence, if I apply here Gn minus 1 and then Gn minus 1, then what can I say? I can say then in such a case, if I do it, I'm getting that An, which will be equal like Gn minus 1 Gn An is convergent to, of course, to the same limit as G naught minus 1 x naught. No, that means it converges, and call that one A naught, and clearly, and since A is closed, we have here that A0 belongs to A. Okay, therefore, by continuity of the multiplication, we have that. Just simply write it down. An Gn is convergent to, okay, Gn times G0 times to A0, which is equal G0 minus 1 G0 x0 equals x0 belongs to G of A. Good. So how to prove this? How we conclude the other proof of the property? It's simple. So now, so let's say proof of this proposition. So proof of the proposition. So notice that for any K subset of G, always closed subgroups, Xk is a closed subspace of X. So, by lemma, x, and I put here bracket like that, a k in bracket, which is actually g of xk, is also closed. And we just observe in such a case, we are getting here that HA, that XH is equal, and what it is equal. So this is the XH, and we just have to subtract from this minus, and I said union over all K orbit type, which is strictly larger than H, and then this will be XH. And what is important here, that this is a finite, so maybe I write it down. So this is a finite union, because there are only finitely many orbit types by assumptions, and this one is closed. So the union, finite union of closed sets is closed, so that means this set is is closed in X, so XH minus closed set is open. And we are done. And we are done. So maybe a couple of remarks, because some particular types of the G spaces will play a role in this theoretical development. So let me continue with the definition. A smooth manifold M, which is also a G space, is called a G-manifold if our multiplication G action on M, if this action, put it like this, G action on M, which is we denoted by M, it is like a G times M, and now goes to M. So G is a manifold, that's a Lie group, M is a manifold, product manifold, M is a map. So in such a case, we assume that this is a smooth map. Is a smooth map. Maybe let's put a couple of the properties of this G-manifolds, and let me not to prove them, and let me point out that all the proofs of these facts can be found in the literature. There is a literature, and I understand it can be scattered. Some things are in the one place, some things in another place. So that's why we are preparing a new book, a new publication, which we would like to make it totally independent. That means we would like to collect all and complete all the necessary, let's say, theoretical material, especially related to the G spaces, that could be considered as the fundamental for our future developments of the G theoretical notions. So in this case, all these proofs of these facts that I mentioned and not proving will be available in this textbook. So we believe that this textbook will be completed within this year, during this year. So I think it will be available as early as 2021. For a moment, let's say just simply refer to the literature, as the book is not published yet. Start with theorem. Let M be a G-manifold okay, then we have? So we started A. If G acts freely on M, then the space of all orbit, we call this the orbit space. So what is this one? So maybe I should write it down. So this is M divided by G, means simply the space of all possible orbits. So that means X is an Gx is a, not good. You see, we have to be very careful. That's this simple. So this is equal to the set of this orbit such that X belongs to M. So those are the orbits, the space, the orbit space, we call it the orbit space, the orbit space, the orbit space is a manifold, it's a smooth manifold, is a smooth manifold. This is a smooth manifold. Let's select this B. Suppose that if H is any subgroup, possibly the whole group, then we have also that MH, the fixed points, H fixed points, is also a smooth manifold, is also a smooth manifold. And maybe C, if M is compact, then M has only finitely many orbit types. So, in our case, put here like this, therefore, if M is compact, then MH is a submanifold, but in this case an open set of a manifold is a manifold, so you can write it down. MH is also a submanifold, on which let's put it like this, WH acts freely, so MH divided by WH is a smooth manifold. Yes, I know there is a couple of the issues related to the last point, so mainly I should explain it more carefully, more completely, and let's do it like this. So let's simply notice, make a couple of observations, so maybe remark. So suppose that we have here the subgroup H is subgroup of G, and we have here X a G space, then we have here the set of all, this is fixed points, so this is the set of all X belonging to X, such that for H belonging to H, Hx is equal to X. So it is clear in general XH is not G invariant. but it is an H invariant. Indeed. So let's write it down. So what does it mean? So just recall that X belongs to the HH. This is the same as the condition standing in the here. So this condition, you see, this is this condition. So this means simply for every H belonging to H, Hx is equal to X, or you can rewrite it down that the isotropy of X is larger equal to H. So that one's okay. So suppose we have a G that belongs to NH. Then, of course, I take this condition here, and I say, what is the isotropy of Gx? So this one is equal to G, Gx, G minus 1 by the property of the isotropies. And that one is clearly larger than Gh, G minus 1. And since since G is in the normalizer of H, so that's equal to H. And definitely that is equivalent to say that G of X belongs to the XH, so we just prove it. So that's definitely true. So this is clear. And since H acts trivially on XH, that means there's no action. It means simply Hx is equal to X, as it's written above. This action can be extended or defined, can be carried on WH. Namely, we can define that means simply the coset, left coset, so right coset, no, left coset of H acts on X just simply by multiplying G of X, where G belongs to NH, and that one X belongs to the XH. So this is well-defined action. So yes, we have here the action on WH on the XH. And of course, now, in addition, notice that WH acts freely on the XH. Yes, indeed. Yes, indeed. So let me write it down exactly what it is. So suppose here that we have here X belongs to the XH, so that means G of X must be equal to H. No, equals. It's not written clearly. Equals to H. And now I take the coset GH from the WH, and we write it down. GH acts on X just simply by taking Gx. So this is the definition of X. So then, let me go to the next page, and we have it. So the isotropy with respect to the Wiles group action of this X will be nothing else than this will be the set of all GH of all the cosets such that G of X is equal to X. But that one we can be written like this. This is GH, such that G definitely must belong to H, because H is equal G of X in our case. X is equal to this case. That implies that this is just simply equal X, and which means this is a coset. This is a coset of a unit element of neutral element. So this means H is a neutral element of WH. And that means we just proved that the action is 3. So WH acts freely. WH acts freely. Let's go back and let's look again on the last statement about the smooth manifold. So let's see again. What do I see? M is a compact manifold. So yes, we have it. So we know that MH is an open set of MH. That's a smooth manifold. That one, MH in the bottom, is an open set in MH. That implies that open set of a manifold is a manifold. Yes, it is a manifold. And here we have here that the WH acts on that set freely. So we go again, and you see we have a statement in the previous one. If G acts freely of N, then M divided by G is a smooth manifold. That means the set set of all orbits equipped with the quotient topology has a structure of a manifold. Let me mention that in order to prove in order to prove A, one needs a few more things about the smooth actions. One of those facts is the existence of this so-called slides to the orbit, and it allows, in such a case, to create local coordinates on the quotient space, on this orbit space. In this case, that one. On that one. So let's think about a couple of examples, maybe one example for a moment, and just to illustrate the concepts that we have introduced. So I start and write it down. Example. This looks like an example. Example. Now it's better. Example. So we put. So our space X, I take like complex numbers, means we'll be using the complex notation, but actually for us it is a two-dimensional Euclidean vector space. Our group G will be a dihedral group that we have discussed previously. So this means nothing else than this is number 1, which is the neutral elements. Then you have gamma, blah, blah, blah. This is gamma n minus 1. And then you have kappa. Then you have gamma, kappa, and gamma n minus 1 kappa. Those are the rotations. Those are rotations, which are rotations of the regular polygon n-gon, and those are reflections. And what is gamma? Okay, gamma is a matrix that can be identified. So gamma can be identified with the complex number 2 pi over n I 2 pi over e to the 1. So that's basically a rotational matrix. We have here theta is equal to pi divided by n. So this matrix simply looks like a cosine theta minus sine theta, and this one is a cosine theta. So the action of G is just simply by rotations, by these rotations. And of course, so let me write it down how it will be how it look like if I take action of G on the complex number Z. So this will simply be the simplest possible formula, complex multiplication gamma times Z. Multiplication by a complex number of that type means nothing else than the rotation. We rotate Z, so this is a complex multiplication. And then here we have also kappa acts on Z just simply by taking the regular, the usual conjugation. Yes, indeed, if you look at kappa, what is kappa? So kappa, as you remember, it is just a conjugation. So 1 minus 1, 0, 0, 0. So this is a conjugation matrix. Once we have it, we would like to look at the possible, let's say, orbit types in the space, okay, X. So that means we would like to describe, so let's put it our objective, so describe the lattice of orbit types. Maybe make it clear what kind of orbit types, of Dn orbit types in this space X equals R2. That is described here. So we have actually two cases. So we have the first case, we have two cases to consider. So the first case, N is odd, is the simpler one, is a simpler one. So maybe let me make a picture, and the same picture will be like repeating itself. So what I need to do, first of all, I realize that Dn is the symmetry group of the regular n-gon. So let me illustrate this. So I just need to make a nice picture. So nice picture. So this is my circle, and I inscribe in this circle a regular n. N-gon n is odd. So what do I get? I have first vertex. Then I have here second vertex, then I have next vertex, and vertex. Is it? Not nice. And then by connecting them, I'm actually getting something that looks like a pentagon. It's a regular pentagon. Regular pentagon. Okay, so let's compute the isotropies. So here, take the isotropy. So this is the number 1. So I take the number 1, and this is nicely whole line here of real line can be written like this. I can write it down. A is equal, so A is equal, I can write it down. A is a real number. A is a real number. So A is a real number. I can put it times 1. Times 1. So 1 acts trivially on A, right? Yeah. Just think about it. Just 1. So this number. So what is, in this case, isotropy of this A? So it's easy. Anything that moves the point A, namely any rotation which is not trivial, non-trivial rotations, will move it. It will transform this point to a different one. So it is not in the stabilizer, or it's not in the isotropy. So for example, look at A. If I take gamma, it will transform gamma is the 1 into the gamma. Here is the gamma. Here is gamma squared. And this will be gamma n minus 1. Do you see? It takes it to gamma. So among the rotations in the isotropy, I have only one possible element, it is 1. On the other hand, you have also one possible element here, one possible element here, which is a reflection, and that's kappa. Clearly, there are no others. So this is my isotropy. This is my isotropy. So I say, okay. So now, if I take this A and I write it down, what would be? And I put it here like this. And I put here gamma A. So take gamma, apply the elements of gamma A. So what is this one? This will be, accordingly to what we learned, it will be conjugated subgroup. So this will be A. And then this will be gamma minus 1, which is a conjugate to gamma. So we can write it down. This is gamma. And that one is 1 kappa. And here we have here gamma bar. And then you can write it down. Gamma, gamma bar, gamma, kappa, gamma bar. And then you go down. And you are getting here that this one is 1 again, 1, and that one is gamma squared kappa. Gamma squared kappa. Kind of interesting if you look at this particular picture, you can see immediately that these subgroups in certain way are also a type of the subgroups, one rotation, one reflection. So, and that's exactly how this subgroups looks like. So we can also call them dihedral subgroups. So this subgroup, first one, we'll call the dihedral subgroup 1. So this will be like a dihedral subgroup, call it 2, because it corresponds to the second element. So if you move to the next one, you will be getting all possible conjugated groups. So let's say write it down. So notice that the orbit type of elements, and I put here gamma, not gamma, put here like this, GA, such that G belongs to the N and A belongs to R. So this is my X, R exactly the, this is this, is exactly maybe, is, no, I should write it correctly. Belongs to R, sorry for messing up. So notice that the orbit type of elements, these elements here, G, so this will be equal, so this will be, is exactly the conjugacy class of this D1, of this group D1. And here, of course, A cannot be equal to 0. Well, we got something interesting here. So namely, if I go back to this picture, then I'm getting here that this orbit type, which I, like this, where is this orbit type? So these orbit types are here. So we have here like this. Exclude 0, but 0 has different orbit types. Then you have here that one, and then you have here that, no, little different like this one, and this one. Let me see. Not good. Sorry. It has to be careful. I will use help. So making nice pictures is difficult. I have to inscribe the pentagon first. So first I'm getting, so this is my first element, this is my second element, then I have here, then I have here, and then, I extend this up and down, up, down, up. And down. And the red, this red should be more regular. This red spider, that's exactly the space X, and this one is D1. This one here, remove that one here. This will be X D1, X D1, and then you have here Dn, that's 0, and everything else has no isotropies, so everything is the white, the things that are left after removing the spider, so this will be Z1. Z1. So we can write it down. The lattice of isotropy looks like we have here Dn, though this is isotropy of 0, and then you have here isotropies D1, so this is isotropies of real numbers. A belongs to real numbers, and all the other outside this, we put it like this, GA, where A belongs to R, different than 0, and then here we have Z1, and then the lattice is like that. Okay, now we consider the second case. The second case is the case n is even. I will just do it maybe a little faster. So in this case we have here a polygon. Let's make a picture again with the even numbers of vertices. So like this to this to this and this one. So we can identify the dihedral rotations. So this will be gamma, gamma square, gamma and minus 1. And then we can now notice that if you extend these red lines to infinity, remove the origin, and we get the spider here. So this will be exactly the same thing as before. This will be X. So this is the red spider. So let me write it in red. This will be X, and this will be D1. And D1 again is nothing else than 1 and kappa. But on the other hand, there is another spider here that is not of the same orbit type. Namely, you take this spider in the middle, like it was before, except my picture was not nice. My picture was very ugly. I didn't get this. And of course 0 is here this is different. This one is the isotropy of 0 is always the whole group. So this will be the so-called D1 tilde group, which is nothing else than this is 1, and the reflection is gamma kappa. You can see that these two subgroups are not conjugate. They are not conjugate. That's why we are getting 2 orbit types. So then, of course, everything else that is outside here will be Z1. And our lattice of the isotrope, let's say orbit types, looks like this. This will be like a D1. 1. This one will be D1 tilde, and this will be Z1, Z1, and you have here these spaces. So the red one is D1, and the blue one is X D1 tilde, tilde. Yes. So notice a couple of things. This is actually a nice thing to observe, that if, notice, that if the cardinality of, maybe you should write it down without if, that the cardinality of the conjugacy classes of the H is equal to 1, that means H, there's only one such a subgroup that is conjugated to H, if and only if H is a normal subgroup of G. So this is normal subgroup. So it clearly tells you that, yeah, this class actually is only for not normal subgroups contains more than one element. So so we will be observing more properties in a moment. So the next notion, let me introduce it here, will be the notion of the so-called NLH numbers. So put it like this, numbers. And I call it NLH. So remember, we are always talking here about the G is a compact Lie group. This is a compact Lie group. And in our case, suppose we have here a subgroup, another subgroup of G, which are related. Can we put and we put it like this, N LH, by the definition, is the set of all G belonging to G such that GL G minus 1 is smaller equal than H. So, in general, this is not a subgroup of G, so I should say like this. In general, NLH is not a subgroup. It's not a subgroup of G. But we have several properties. NLH is a closed subset of G. Okay, indeed. Suppose we have here Gn belonging to NLH, and assume that Gn converges to G0. Here, this condition here is equivalent to write that for every A belonging to L, I have here Gn A, Gn minus 1. So that's an element L belongs to H. That belongs to H. And since H is closed, if I pass with n goes to infinity, I will be getting here that G0A, G0 minus 1 also belongs to H. Wow, for every A belonging to L, so that implies that G0 belongs to the NLH. And we got here the statement. Yes, so that's our first observation. Second observation, B. So the set NLH is invariant with respect to the left NH action on G. And what does it mean? That simply means for every H belonging to the NH, if I write it down H, then I will be getting that H applied to LH is exactly equal to NLH. Okay, so let's prove it. So I have to switch the page. So take G belonging to NLH. So what does it mean? That GLG minus 1 is smaller equal than H, and consider HG and take L, and this will be HG minus 1, and check out what happens, what it is. So this will be definitely the same as H, and this will be GL, and this will be G minus 1, and that one is H minus 1. But the first one, you see at the top here, we have here that one. So that implies that this was smaller equal, this is H, and this is H minus 1. But H is in the normalizer, so H belongs to the normalizer of H. So in such a case, that's equals to H. So done. So yes, indeed, this is it. And also notice this one, C. Since H and NH are closed subgroups of G, write it clearly, acting freely on NLH, we obtain that NLH divided by NH and NLH divided by H are well-defined orbit spaces. We define the orbit spaces. And what else we know? Those are the, did I prove that this is closed set? So closed set, and this is subset. This closed set is a subset of G. So every closed set is actually, the NLH is actually compact, so that means this is a compact space. So those are all compacts obtained, well-defined spaces. And now we can introduce our main definition. I put it in red. Maybe I write it first, but that's one of the main definitions that will be rely a lot on it. So by the definition, this will be cardinality. Absolute value is cardinality. And LH, and this one is divided by NH. So this is cardinality. Cardinality. And let's put it in red. And we'll call it, this is the so-called number NLH. Possibly infinity. If this is an infinite set, then this will be infinity. So the next observation is D, that if we will take the particulars, so notice that this particular space in LH divided by H is a right, and here we have a WL space. So right space, so that we have here an action on the right. So let me write it down. Let's say like this, indeed. So indeed, I need to put it like indeed. A belongs to the NLH again, if and only if ALA minus 1 is belonging to H. So contained, it's contained. So this is smaller equal to H, contained. So now take G belonging to NL, and then let's see what happens. So how it acts? It acts on the right. So this is AG. Take L, and this will be AG minus 1. And this will be the same as A, and this will be GL, G minus 1, and that one is A minus 1. Since the first one, we have here that property, so we can rewrite it down, smaller equal to AH, sorry. No. G belongs to the normalizer. Sorry, this one. So we look at that one. This belongs to the normal. So this is equal to L. So in such a case, I'm getting AL, A minus 1. So clearly smaller equal to H, and we're done. So this is action. So the action, the NL action on NLH is well defined. Which action? This will be right action. Right is well defined. Is well defined. Is well defined. Just notice, and I leave it as exercise because something has to be also left to the reader, okay, to the audience. Notice then if G, notice that in this case that if G belongs to L, then you have actually, remember this is the orbit space, so then you have here H applied on AG. It's like a right, it's like a right coset. Is actually in this case equal to H A. Sorry, HG, yes. No. do. So you take A belongs to L, then you take H, AG is the same as HG, axe from the left, sorry, axe from the left, yes. No, good, G belongs to the NL, then you have here H, A, G will be the same as AG. Check it. Not G, GA. GA. Where's A? A belongs to the N and H. Am I right? Yes. That means L acts trivially on N, L, H divided by H. Yeah. Let me check because everything says to me. Let me see. So G belongs to, again, the action is here on that side. So the G is from that. So G is from the L. G is from L. So that thing I apply it. So I'm getting here. This is G. Okay. Yeah, you can check it. Yes. Okay. Okay. So in such a case, we are getting here that indeed we have here, so we obtain that WL acts on the right, so that obtain the right action of WL on NL H divided by H. So this is now a time for another insertion. I will insert a new definition. So definition. Let X and Y be two G spaces and F a function, a map. We say that F is G equivariant map or simply a G map if, so the first condition is that F is continuous, and the second condition is that for every G belonging to the G and for every X belonging to X, we have here F Gx is equal Gfx, commutes with F. So this is called the equivariance. So we have the simple observation, put it like a proposition. let f that goes from x to y be a G map, and H is arbitrary subgroup of G. Then we have a f of x h is actually subset of y h, and b, the map f of h, which is by the definition f restricted to f of to xh, to these fixed points, which now of course is well defined from fixed point x to the h to the y to the h, is an h equivariant therefore, because H acts trivially on these subspaces, it is WH equivariant. And the proof is really simple. Proof, you probably notice I'm doing all the simple proofs. So take this one here. So recall, this means simply if and only if g of x like that is larger equal than h, then of course a for every h belonging to h, we have here f of x is the same as f of hx, and then this one is equal to f of x. So that implies that h belongs to the g of f of x, and this is equivalent that g f of x is larger equal than h. And that of course means f of x belongs to the y h. Done. Done. So let's return again to the NLH spaces. So write it down, proposition. So proposition suppose we have here L smaller equal than H smaller equal than G, then the map, and I put here like this, F defined from N, L, H, and this goes to H. And now this is the orbit space, so those are the left cosets. And this orbit space is actually also a G space. So in particular, I can take the fixed point space, L fixed point space. So I define that the map F from here to there by the formula that means simply F. So now I take the orbit here, H on G. So the G belongs, of course, to NLH. So this will be equal, and I defined it like this, G minus 1 of H, where G belongs to the NLH. So this is a well-defined map. So what we actually see here, that this map is WH equivariant homeomorphism. WL equivariant homeomorphism. So that means in this case, here is the right WL space, and that one will be left WL space. And I don't want to do these verifications because it will consume too much time. However, let's say there are many textbooks where it is nicely proved, including the book which is available everywhere. This is Kawakubo. Let's say transformations of compact groups, and the book by Kawakubo, and you may check it. But however, we may play with the easy part of the proof, namely we can basically assume that, suppose this is G belongs to the NLH. So of course, recall this means simply that this is always this condition. So now that means also that for every L belonging to L, I have here GL, G minus 1 is in H. So now you can rewrite it, and you write it now L belongs to L, and this is GL, G minus 1. And I put here H, smaller equal than H. That's the same thing. And then you can rewrite next, you can write, but that means the same, because here I can move one G on the other side, so that means L, G minus 1. L is a small L, L is a small L. So this is L, G minus 1, H, smaller equal 10. And I have here G minus 1, H. And then you look, wow, those are the left cosets, and left cosets are either the same, either disjoint. So in such a case, it means that this can be changed to equals, and we are getting here the conclusion, so that G minus 1H actually belongs to GHL, because that means exactly that property. So that means the map is well defined. The map is well defined. And I will stop it here, and I hope to continue this topic next time. There is a few more observations about the NLH spaces that we will need to complete, and I'll also prepare for the next time the additional references. I'll put the references here so we could have a better way to, let's say, to address the issue of unproved statements. And thank you for now. Thank you.